Hi guys, welcome back to Z Physics. Today we are going to be looking at some of the hardest physics problems in the world, namely the problems from the International Physics Olympiad. The problem which we're going to be looking at today is from the 38th International Physics Olympiad, which took place in Iran in 2007. The problem is on the very exciting topic of black holes. You can find a link to the actual problem and to the mark scheme in the description below this video. Okay, well, let's get started on the very first problem 1.1, which is about dimensional analysis. As with most Olympiad problems, it starts with quite a lot of information about the phenomenon about the question. In this case, there's quite a lot about dimensional analysis, so there's a lot of general information about it. Notice that they're giving us a few things. For instance, they're giving us a way of writing out the base units. So if you guys are used to write them as the units for velocity, let's say as meters per second, over here we are given them as the units of length per the units of time, without actually having specified the base units. So they're asking us for the first question, 1.1, to find the dimensions of the fundamental constants. So Planck's constant, the speed of light, the universal constant of gravitation g, and Boltzmann's constant kb in terms of the dimensions of length, mass, time, and temperature. Well, let's get started. Let's start off with the base units of Planck's constant. The easiest way to get the units of Planck's constant is just to use the energy for the formula of a photon, which is E is equal to h times F. Rearranging for Planck's constant, we get that h is going to be equal to E over F. Now, this means that the units of h are going to be equal to the units of energy divided by the units of frequency. The units of energy are actually given in this equation, so mass times length squared divided by t to the power of -2. So I'm just going to write them down over here, ml squared t to the power of -2. If you're curious where this expression actually came from, just over here on the side I'm going to write this. For instance, E is equal to a half mv squared. This is just the formula for kinetic energy. The half is going to have no units. M, the mass, is going to have the units of mass. V is going to have units of length per time, and then all of that is squared, and this is really equal to ml squared divided by t squared, which is equal to ml squared t to the power of -2. Okay, cool. So I have the units of energy which are here, and I just need to divide them by the units of frequency, which are t to the power of -1, and this is because frequency is 1 over the time period, like so. So mathematically this is going to give us ml squared t to the power of -2 times t, like so. So this means that the units of Planck's constant are ml squared t to the power of -1. So Planck's constant is done. Next one up is the speed of light, c. Well, that's an easy one. The speed of light is just normally measured in meters per second. So this is going to be L t to the power of -1. Next one up is the universal constant of gravitation, g. For that, we're going to use Newton's law of gravitation, which says that the magnitude of the gravitational force is equal to gmm over r squared. What I'm going to do is simply just rearrange for the gravitational constant, and this will be equal to F times r squared divided by the product of the masses. Now, because this force here, assuming that's the only force acting on that object, is going to be equal to ma times r squared divided by the product of the two masses. We're going to cancel out one of those masses, and now we're ready to find the dimensions of G. So let's have a look. The dimensions of G are going to be equal to acceleration. Well, that's simply length meters per second squared, t to the power of minus 2, multiplied by length squared, which is r has the dimensions of length, and we're going to divide this by the units of mass, which are normally the kilograms, so we're going to keep that as m. So this is going to equal to L to the power of 3, t to the power of minus 2 times m to the power of minus 1. Next one up is the universal constant of gravitation, G. For that, we're going to use Newton's law of gravitation, which says that the magnitude of the gravitational force is equal to gmm over r squared. What I'm going to do is simply just rearrange for the gravitational constant, and this will be equal to F times r squared divided by the product of the masses. Now, because this force here, assuming that's the only force acting on that object, is going to be equal to ma times r squared divided by the product of the two masses, we're going to cancel out one of those masses, and now we're ready to find the dimensions of G. So let's have a look. The dimensions of G are going to be equal to acceleration. Well, that's simply length meters per second squared, t to the power of minus 2, multiplied by length squared, which is r has the dimensions of length, and we're going to divide this by the units of mass, which are normally the kilograms, so we're going to keep that as m. So this is going to equal to L to the power of 3, t to the power of minus 2 times m to the power of minus 1. And finally, we're going to have a look at the dimensions of Boltzmann's constant. For that, we're going to use the formula for the kinetic energy of a single particle in the kinetic theory of gases, which says that the kinetic energy, let's call that EK, is going to equal to 3/2 times Boltzmann's constant times the temperature in Kelvin. What I'm going to do is just rearrange for Boltzmann's constant, which is going to equal to the kinetic energy divided by the temperature times 2/3. This means that the units for Boltzmann, or the dimensions of Boltzmann's constant, are going to be the same as the ones for kinetic energy, which are given over here. So that's going to be mL squared t to the power of minus 2. Don't confuse the t for the units of time with T as the symbol for temperature. The dimension and the unit for temperature is Kelvin. So this will be divided by Kelvin, and the way also I'm going to write this is as mL squared t to the power of minus 2 kelvins to the power of minus 1. And we are done with 1.1, which was a nice and easier start to this Olympiad problem. Let's have a look at the rest. Determine the dimension of Stefan-Boltzmann's constant in terms of the dimensions of length, mass, time, and temperature. Our starting point for this question would be to write down Stefan-Boltzmann's law, and this says that the luminosity of an object is equal to Stefan-Boltzmann's constant multiplied by the area multiplied by the temperature raised to the power of 4. So what I'm going to do is rearrange for Stefan-Boltzmann's constant, which is equal to the luminosity, which is equal to the total power radiated by a stellar object, divided by the area times the temperature raised to the power of 4. Now remember, luminosity is actually power in astronomy, really. So this is just equal, has units of energy per time, like so, divided by the area times t to the power of 4. This means that the dimensions of Stefan-Boltzmann's constant are going to be the dimensions of energy per time, so divided by time. If you remember from the first question, the dimensions of kinetic energy are ml squared t to the power of -2, so I'm going to divide that by t yet again, and this will give me dimensions of ml squared t, and rather than t to the power of -2, I'm going to write t to the power of -3. I'm going to divide that by the dimensions of area, which are meters squared, so it's going to be length squared, times T here stands for temperature, so it's going to be kelvins raised to the power of 4. We're going to cancel out those guys here, and what we are left with is T to the power of -3 kelvins to the power of -4. So we've already done 1.2. We've determined the dimension of Stefan-Boltzmann's constant, which are written just over here. Those are the units of mass times the units of time raised to the power of -3 divided by the units of Kelvin to the power of 4. So we've done this. Now let's have a look at the next one. Stefan-Boltzmann's constant is not a fundamental constant, so this means that it can be expressed as a product of all the other fundamental constants that we just found the dimensions of raised to a certain power. You can kind of think as all the non-fundamental constants as being built like built from Lego blocks from the fundamental constants raised to a certain power. Well, let's see whether we can figure out those powers. They've conveniently set this factor, multiplying it equal to 1, and you can see that this is why I've written down Stefan-Boltzmann's constant as follows. All the fundamental constants raised to a particular power. Well, let's first off just express Stefan-Boltzmann's constant in terms of the dimensions of the fundamental units. First off is Planck's constant h, which is just ml squared t raised to a power of -1. So this is h, Planck's constant, and the whole of this is raised to the power of alpha. Next up is c, which is the speed of light. That's the easy one from the last question. So that's just the units of length divided by the units of time, and this will be raised to the power of beta. Next up is the gravitational constant g, and g will have the following units. So that was m to the power of -1 L cubed t to the power of -2, and all of this will be raised to the power of gamma. I'm just going to rewrite my power gamma a little bit more clearly so that you guys don't get confused. My gamma can be written a little bit weirdly sometimes, but that's a little bit better. And finally, I'm just going to express the units of Boltzmann's constant. I'm just literally just rewriting them from the previous question. And Boltzmann's constant was equal to ml squared, like so, t to the power of -2 k to the power of -1, and all of this is raised to the power of sigma. Okay, so we've got a good mathematical problem, and that is that the units of all of these units multiplied, all of these dimensions multiplied, have got to equal m t to the power of minus 3 k to the power of minus 4. We like a good challenge. Let's solve it. Okay, now the next thing which I'm going to do is literally just expand out those brackets. So this expression over here on the right will be equal to m to the power of alpha, L to the power of 2 times alpha, t to the power of minus alpha, L to the power of beta, t to the power of minus beta. Then we have m to the power of minus gamma, L to the power of 3 times gamma, t to the power of minus 2 gamma, and finally we have m to the power of sigma, L twice sigma, t to the power of minus 2 sigma, and kelvins to the power of minus sigma. So it's quite a long expression, and all of this is going to have to equal m t to the power of minus 3 k to the power of minus 4. Next step will be to simplify the right hand side of this equation. As you can probably agree, it's a little bit messy at the moment on the right hand side, so let's just quickly simplify this. So let's gather together all the factors of m. So I have m to the power of alpha, m to the power of minus gamma, no m to the power of beta, m to the power of sigma. So let's put them all together. Overall, this will be equal to m to the power of alpha minus gamma, like so, and plus sigma, multiplied by L to the power of 2 times alpha plus beta, like so. Where's our next L? 3 times gamma, so plus 3 times gamma, and plus 2 times sigma, like so. And our next expression is for t, like so, which is going to have powers of minus alpha. Our next t is minus beta minus 2 times gamma minus 2 times sigma. Finally, we're going to have an expression for k, which is just minus sigma, because as we can double check here, there are no more factors of k on the right hand side of this equation. Now together, all of this will have to equal m t to the power of minus 3 k to the power of minus 4. This means that individually, plus alpha minus gamma plus beta is going to have to equal 1, plus 2 alpha plus beta plus 3 gamma plus 2 sigma will have to equal to 0, because there is no factor of L on the left hand side. This expression here for the power of t will have to equal to minus 3, and minus sigma will be equal to minus 4. Together, these expressions will allow us to write a system of 4 simultaneous equations that will allow us to determine those constants. Well, let's do this. Okay, so let's write down our system of 4 simultaneous equations. So let's start off with m. I'm going to write down that alpha minus gamma plus sigma will have to equal to 1. So essentially this term over here equals to that. The factor for L, as we've noted before, is going to have to equal to 0 because there's no L on the left hand side. So what I'm going to write it down is that 2 alpha plus beta plus 3 gamma plus 2 times sigma is going to equal to 0. After that, we're left with minus alpha plus beta, minus beta. Always be careful with your minus signs, minus 2 times gamma minus 2 times sigma, like so. This will equal to minus 3. And finally, a simple expression for our power for the Kelvin, and that is that minus sigma will be equal to minus 4. And a different way of just writing the same expression is that sigma is equal to 4. Okay, now we have a system of 4 equations and 4 unknowns. Well, now we know one of them. It will allow us to find the other 3. Let's do this. The first thing that we can do after we have this system of equations would be just to substitute the value of sigma in all of those equations. So rather than just alpha minus gamma plus sigma, I'm going to just write down plus 4 like so. On the equation just here, it will be plus 2 times sigma, which is plus 8. On the one below, it will be minus 8. Well, let's start solving these equations. So let's start off with the first one. I'm just going to rearrange for alpha. And the first equation will give me an expression for alpha in terms of gamma, which will be equal to plus gamma. When I bring it to the other side, the 4 is going to turn to a minus 4 plus 1 will give me a minus 3. So we know that alpha is equal to gamma minus 3. And then I'm going to substitute this expression for alpha into the second expression. So into the second equation. So what I'm going to get is 2 times alpha, which will give me 2 times gamma minus 2 times 3, which is 6, plus beta plus 3 gamma plus 8 is equal to 0. Let's do a bit of simplification. So what we're going to get is 2 gamma plus 3 gamma is equal to 5 gamma. Minus 6 plus 8 is going to give me plus 2, like so. And finally, we have plus beta remaining, like so. Now, all I'm going to do then is just rearrange for beta. And I'm going to get that beta is equal to 5 minus 5 gamma minus 2. Now I'm ready to substitute an expression for both alpha and beta into this third equation. This will enable me to find the actual value of gamma. I know that alpha is gamma minus 3. I know that beta is minus 5 gamma minus 2. So let's do this. Okay, so focusing on the third equation over here, which I'm going to rewrite at the bottom. But rather than alpha, what I'm going to say is that alpha is gamma minus 3. Take away or multiply this by minus 1. So minus alpha will be equal to 3 minus gamma. Minus beta will just be equal to 5 times gamma plus 2. Minus 2 times gamma minus 8 will be equal to minus 3. Now we're ready to do a little bit of simplification. So what we are going to simplify, let's start off with the gammas first of all. So minus gamma plus 5 gamma is going to give us 4 gamma. Take away another 2 of that, so we're going to get a factor of 2 times gamma. Let's do the digits next. So 3 plus 2 is going to equal 5. Let's take the 3 on the other side, and we're going to get plus 8. What we're left with is just minus 8, which will conveniently cancel out. And we've taken care of everything in this equation. We're going to get quite a nice simple result that 2 times gamma is going to equal to 0. In other words, gamma will be equal to 0. Now that we know that gamma is equal to 0, we could easily find the other factors, and I'm just going to write them out with a different color over here on the side. So if gamma is equal to 0, alpha will be 0 minus 3, so this means that alpha will be minus 3, beta will be minus 5 minus 2, minus 5 gamma minus 2, so that's just going to be minus 2. We know that gamma is 0, and finally sigma like so. Well, we know that this is 4 from the beginning of the problem. So we've almost solved this problem. We've managed to find the coefficients, and what we can do finally really is just to rewrite this equation so in a way that the Stefan-Boltzmann's constant is expressed in terms of those fundamental constants. I'm just going to do this over here. So Stefan-Boltzmann's constant will be equal to Planck's constant raised to a power of minus 3. The speed of light, which has been raised to a power of beta, which is minus 2, like so. And the gravitational constant raised to the power of gamma, which is 0. So anything raised to the power of 0 is 1. So I'm just going to not include that in this expression. And Boltzmann's constant, let's call that KB, raised to the power of 4. An alternative way of writing this, of course, is that Stefan-Boltzmann's constant is equal to KB to the power of 4 that's been divided by h cubed and the speed of light squared, which is our final answer. A really elegant answer indeed. Okay, folks, so hopefully you found this useful. Over the next week, I'm also going to film the remainder of this question on the physics of black holes. If you have found this video useful, please consider subscribing and hitting the like button. Thank you very much for watching, and I hope this was useful.